Hey, welcome back to partial derivatives. We're still going. So this is number 2. Okay, so let's talk about some notation real quick, and then we'll do another example or two. So in addition to this subscript notation that we did last time, f subscript x, f subscript y, there are some other ways to denote partials, and I want you to be comfortable with all of them, because when you're doing your homework and your exams or whatever, I want you to be clear, oh, that's what they're asking me for. So another way to denote the partial derivative of f with respect to x is df dx. And notice these letter d's have melted stems, which are kind of curvy, and that is key because you need to learn how to draw those because that's denoting a partial derivative. So df dx. So another way you might see this is the d dx, where the function is denoted f of xy. That's also common. And sometimes, since your function might also be denoted z, they may just say they want dz dx. But they're all asking for the same thing, partial with respect to x. So the partial with respect to y has similar notation, df dy, or d dy fxy, or dz dy. So a little bit extra here, sometimes you'll be asked to evaluate your partial derivative at a particular point, at that specific point. So evaluating at a point, which means basically you're going to substitute some things in there for x and y, plug stuff in. So you might be asked to, say, for example, evaluate your partial derivative of f with respect to x at the point AB. So that's one way to do it. They'll just say AB instead of xy. Another way, using this differential notation, they'll put df dx with a vertical line, and right at the bottom of the vertical line, they'll put down the point that they want you to plug in. So similarly for the partial derivative with respect to y, you'll see similar notation. Okay, so let's do another example. So they want us to find the first partials here, fx and fy, for this function, z equals f of xy, which is x e to the x squared y power. And then we're going to evaluate both of those partials at the point 1, ln 2. Now this is going to be a little bit trickier than the last problem, so pay attention to see why that's the case. So put on your glasses. These glasses, we're going to look through, we're going to hold y constant. It's going to look like y is just a pure number to us temporarily while we're taking the partial of f with respect to x. So I want you to notice something here. We have x times an exponential, and the exponential has an x in the power. So what does that mean? We're going to need to use the product rule. Remember that? So in order to use the product rule here, we're going to first take the derivative of the first factor, x, with respect to x, which is just simply 1. Multiply that by the other factor, which is the exponential e to the x squared y, plus x times the derivative of e to the x squared y power with respect to x. So you remember how to take the derivatives of an exponential. So the derivative of e to the u is e to the u times u prime. So u prime for us will be the derivative of x squared y with respect to x. So remember, y is just a constant multiple, so it comes along for the ride, and the derivative of x squared with respect to x is 2x. So 2xy is the derivative of the power there, x squared y. And then cleaning this up a little bit, you can factor out a common factor of e to the x squared y, and then you'll have 1 plus 2x squared y there. So there's your first partial of the function f with respect to x. We needed the product rule. Now, take off these glasses, put on a different set of glasses, because we're going to take the other partial. The partial of f with respect to y. So what does this mean? In your new set of glasses here, you're going to hold x constant. So it's going to look like x is a pure number everywhere, and you're going to take the partial of f with respect to y. Do we need the product rule now? Turns out we don't. Why not? because this is a product of something with x times the exponential, and x right now, because of this special set of glasses, it looks like a constant, like the number 2. So no product rule needed. X is just a constant multiple, so you'll multiply that with the derivative of the exponential with respect to y. So the derivative of e to the u is e to the u times u prime. So what is the derivative of x squared y with respect to y? It's just going to be the constant multiple x squared, and then multiplying all these powers of x and rewriting it with a single power of x, we now get the first partial with respect to y, x cubed e to the x squared y power. Okay? What does it mean, these partials? And here is the geometric interpretation. If you are on, say, some surface here, maybe a mountain, and you're standing at a point, the df dx, or the partial with respect to x, is giving you the slope in the positive x direction. So whatever the slope is there of your mountain, if you will. So what about df dy? It's giving you the slope in the positive y-axis direction. So that's the geometric interpretation for partial derivatives. And we're going to use that in our next example. So let's go ahead and quickly do this next example using this geometric idea of slopes in the positive x and positive y-axis directions. So take a look at this easy function of two variables, negative x squared over 2 minus y squared plus 25/8. We're going to evaluate both at the point. They want us to find the slopes in the x and y direction. That's just a fancy way of saying, go find the first partials. So the slope in the x direction is fx. So let's go ahead and take the partial of f with respect to x. So put on your special glasses, you're going to hold y constant, and you're going to differentiate with respect to x. Here we go. What is the derivative of negative x squared over 2 with respect to x? Well, it's negative a half times the derivative of x squared with respect to x. That's just 2x. And we're done with that term. How about the derivative of negative y squared with respect to x? That's 0. And of course, the derivative of 25/8 is 0. So after we clean this up and simplify, we get the slope is negative x. Okay? The slope in the y direction will be the first partial of f with respect to y. And after we get done with this, we'll evaluate both at the point. So when you differentiate negative x squared over 2 with respect to y, since there are no factors of y in this whole term, that's 0. And then the derivative of minus y squared with respect to y is negative 2y, and of course 25/8 has a derivative of 0. So this is just going to be negative 2y. Now, if we're going to evaluate each of these at the point, 1/2, 1, 2, they're giving us the z coordinate, which is nice, but we don't need that because neither of these partials have the variable z in there. So really what we're doing is we're taking fx and evaluating it at the point 1/2, 1, which is in the xy plane. And that's going to be negative x or negative a half. The negative has a meaning here. It means that if you were standing on the mountain and you were looking in the positive x-axis direction, you would have a negative slope, so you'd be able to ski downhill. Okay? If you evaluate the other partial with respect to y here at the point 1/2, 1, we get negative 2y and negative 2. So we're also having a negative slope in the positive y direction. In fact, it's going to be even more of a downhill. So if you're a hotshot skier, you probably want to ski down the direction of the positive y-axis, so you'd have a steeper slope to ski down. More fun. And that concludes the second half of the partial derivatives lecture. Tune in and I'll finish up this example next time.